So the Eratosthenes sieve is a very nice little process that allows us to eventually find all prime numbers, at least theoretically speaking, because practically speaking, after a certain point, it is so slow that it is of no practical use. So the principle is the following, that if n greater than 1 is a natural number, and we delete or sieve out, if you like. That's the idea of a sieve, that you let unwanted items go out, and what is left behind is what you want. And if we delete all multiples of prime numbers, and here I should say strict multiples, meaning don't delete the number itself, of primes that do not exceed square root of n, along with 1. Also, don't forget to delete 1. Then we are left with all prime numbers that do not exceed n. Okay, so basically you need to use knowledge of all prime numbers that are less than or equal to square root of n in order to find all prime numbers that are less than or equal to n. Okay, so if you know the prime numbers that do not exceed 10, then you can find all prime numbers that do not exceed 100. Once you know the prime numbers that do not exceed 100, you can find all prime numbers that do not exceed 10,000. Once you know the prime numbers that do not exceed 10,000, then you can find all the prime numbers that do not exceed 10,000 squared. That's 100 million. So you see, soon enough, you will find all prime numbers, at least theoretically. Okay, or every prime number will be identified in this process. And of course, here we use a statement for which there is a separate video, according to which if we have a composite number, then there is a prime divisor of it which does not exceed its square root. So let's see how this is done in practice. So in order to do this, it's a good idea, first of all, to write down all the numbers from 1 to 100. I'm sorry that I'm not pausing the video and do this so bear with me. It will take a moment to write all these numbers down and show how this very early piece of beautiful mathematics works. So I should say here that the prime numbers that do not exceed 10 are 2, 3, 5, and 7. So there's not too much work that needs to be done here, but let's show it. You can certainly not wait for me to write all these numbers down. Just forward the video to the point where these numbers have been written. So this way you don't have to waste your time watching me write those numbers down. It's, like I said, it takes a couple of minutes. And I will stop talking till I have written the other 50 numbers. So please forward the video for about a minute later. Okay, so we've written all numbers down, and here's what we're going to do. So we're going to, first of all, single out the primes that do not exceed 10. So there are 2, 3, 5, and 7. And let's get rid of the number 1, which is known not to be a prime number. And now let's get rid of the multiples of 2. Let's use a green color in order to do that. So this is the full column below 2. All the column starting with 4. All the columns starting with 6. All the columns started with 8. And the full column starting with 10. Okay, now let's use a different color in order to get rid of multiples of 3, technically multiples of 3 that were not multiples of 2 because these have already been dealt with. Okay, so what are the multiples of 3? So we have to get rid of 9, of 15, of 21, of 27, of 33, of 39, of 45, of 51, of 57, of 63, of 69. I go every 3 numbers pretty much, and if it's not deleted, I delete it. Of 75, of 81, of 87, of 93, and 99. Okay, now let's use a different color to get rid of the multiples of 5. What color? Let's get this. So what are the multiples of 5 that have not been already deleted? They just belong to the column below 5. So we have 25, 35, 55, 65, 85, and 95. All other multiples of 5 have already been dealt with. And finally, let's deal with the multiples of 7. Let's use yet a different color for those. I'm not sure if these colors are so discernible, so I'm sorry about that. So the first multiple of 7 that has been dealt with is actually 49. And then we have 56 has been dealt with, 63 has been dealt with, 70 has been dealt with, 77 has not been dealt with, and 84 has been dealt with, and 91 has not been dealt with, and 98 were all set. So now all we need to do is circle the numbers that were not deleted in this process. So what do we have? So we have 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, 97, and that's it. And if we did everything correctly, I believe there are 25 prime numbers that do not exceed 100. So the probability that the prime number less than 100 is prime is exactly, or less than or equal to 100 is prime, is exactly 1 out of 4, or 25%. So now, of course, for this one, we would need we should better use a computer program, since we know the primes that are less than 100. We can use that in order to find the primes that are less than 10,000. And there are some very nice programs that can be found online in different languages. My favorite one is Python, of course, but you can use them in order to generate a few million prime numbers. And that's all. Thanks for watching.